When you look up at the night sky,
Yeah.
it's just so vast.
The sheer infinity of it, yeah.
Exactly. And I think for a lot of us, right alongside that sense of wonder, there's this other feeling, this really primal fear.
Oh, what if?
Right. What if something out there, something we can't even see or control, could just end life on Earth? It's a question that pops up everywhere, movies, myths, you name it.
And that's exactly what we're tackling today, that instinctive curiosity about our own cosmic fragility. But we're not here for Hollywood speculation.
Or those wild rumors you see on social media.
Exactly. We're diving deep into the actual data straight from the scientific community. We want to look at the real probabilities and the actual mechanisms of these potential cosmic threats.
So our mission for this deep dive is really to move past that paralyzing fear. We want to give you the hard data, the perspective you need to, breathe a little easier.
A little easier, but maybe not completely. The universe is still a pretty dynamic place. Look, the short answer is, scientifically speaking, yes, something could happen. But the much longer, and I think way more interesting answer, is the story of our vigilance.
Our scientific vigilance.
That's it. So we're going to break down the 3 big cosmic threats that the research points to. First, the most physical one, asteroids.
Okay.
Then, the technological threat from our own star, extreme solar storms. And finally, we'll get into the really distant but terrifying stuff.
The cosmic monsters.
The cosmic monsters, black holes, and gamma ray bursts.
Okay, so let's unpack this, starting with the one that feels most real. The threat that isn't theoretical at all. It's a geological fact. Asteroids.
It is. I mean, the proof is right there in the rock strata. We know that 66 million years ago, a massive object, something like 10 kilometers across, slammed into Earth.
And that was it for the dinosaurs. It just completely changed the climate.
It's the ultimate proof of concept, isn't it? But here's the thing that often gets missed in all the drama. We don't need an impactor that huge for a global catastrophe today.
So we're not talking about another 10-kilometer beast.
No, not at all. The scientific consensus is that an asteroid of just 1 kilometer in diameter. That's it. That would be enough to cause devastation on a truly global scale.
Just 1 kilometer. What does that devastation look like?
It's mostly about what gets thrown into the atmosphere. All that dust and particulate matter would block out the sun, triggering something like a nuclear winter.
Which would mean agriculture collapses.
Agriculture collapses, supply chains break down worldwide. It would be a complete societal crisis.
That immediately makes me wonder about the odds. I mean, are we just sitting ducks here waiting for the next big one?
Well, this is where the good news comes in. And it's really, really reassuring. For those big 1 kilometer plus impactors, the probability of one hitting us in the next century is extremely low.
And that's not just a guess.
Not at all. This is down to focused science. Agencies like NASA have already found and cataloged more than 95% of these large near-Earth objects. We call them NEOs.
So we know where they are. We know their orbits.
We know their orbits. And critically, none of them pose an imminent threat for the foreseeable future.
Okay, that's a massive relief. The biggest civilization-ending threats are accounted for. But as I was looking through the data, the threat seems to shift. It's not about the known giants.
You're right. The real kind of day-to-day danger lies with the smaller stuff.
For ones we can't see as easily.
Precisely. We're talking about NEOs that are, say, 140 meters in diameter or less. There are just so many more of them, and they are so much harder to track.
And an object that size, it wouldn't end civilization?
No, it wouldn't. But if it hit a major city, say a coastal metropolitan area, it would completely wipe it off the map. A massive regional catastrophe with, huge global economic fallout.
So the dinosaurs were caught completely unprepared. But we're not. We have a plan, right? What do we do when we find one of these smaller rocks on a collision course?
This is where we shift from just watching to active planetary defense, and the research really highlights the success of projects like NASA's DIRT mission.
The double asteroid redirection test.
Right, and the key idea isn't what you see in the movies. We don't want to blow it up.
Because that would just create a bunch of smaller but still very dangerous fragments.
Exactly, a cosmic shotgun blast. Instead, the plan is a gentle nudge.
A gentle nudge. How on earth does a tiny nudge change the path of a giant rock millions of miles away?
It's the absolute genius of orbital mechanics. The DART spacecraft showed that if you hit an asteroid with a precise kinetic impact, you create a tiny, tiny change in its speed, a gravitational push, we call it.
Okay.
Now, if you do that far enough away from Earth, say 10 years before a potential impact, that tiny little difference in speed gets magnified by gravity over time.
So over millions of miles, that tiny nudge becomes a big miss.
A huge miss. It only needs to miss Earth by the radius of the planet. So the key is early detection. Giving that little push enough time to work, it's an incredible piece of engineering, and it should give you a lot of confidence.
Okay, so if asteroids threaten our physical existence, this next threat is completely different. It targets our modern way of life, our digital infrastructure.
Right. We're talking about extreme solar storms.
And this isn't about destroying the planet itself. It's about, sending our civilization back to the 19th century in just a few hours.
That's a pretty good way to put it. What's so fascinating is that our sun isn't just a stable, quiet ball of light. It's constantly throwing out clouds of charged particles. That's the solar wind.
Sometimes it does more than that.
Sometimes it has massive eruptions. These are the things we call solar flares and, more importantly, coronal mass ejections, or CMEs.
And it's important to know the difference there because people tend to use those terms interchangeably.
That's a critical point. A flare is the initial flash of light and radiation. It travels at the speed of light, so it gets here in about 8 minutes. It can cause some radio blackouts, but it's not the main threat.
The main threat is the CME.
The CME is the real danger. That's the actual cloud of magnetized plasma that gets ejected. It travels much slower.
So it hits us hours or even days later.
Right. And if a massive CME is pointed directly at Earth, those charged particles slam into our magnetic field and induce these enormous electrical currents in any long conductor.
Like power lines.
Power lines, undersea communication cables, pipelines, anything long and metal.
And we know this isn't just a theory. It has happened before. The big one everyone points to is the Carrington event in 1859.
The 1859 event was spectacular. The auroras, the northern lights, they were seen all the way down in the Caribbean. People were reportedly reading newspapers at night by the light of the aurora.
Wow. And what did it do to the technology of the day?
Well, it completely overloaded the telegraph networks. Operators reported sparks literally jumping off their equipment. Some of them could even send messages after they disconnected the batteries, just running on the current from the storm.
So if that was the damage then to a simple telegraph system, what does that mean for us today in our, hyper-connected digital world?
It would be a catastrophe. The estimated economic damage is in the trillions of dollars. But forget the money for a second. Think about the real-world impact.
Okay.
We're talking about the massive high-voltage transformers that are the backbone of our electrical grid. Many of them would be fried permanently,
Leading to a blackout that isn't just for a few days.
we'd be looking at a multi-year recovery period. And think of the cascading failures. No electricity means no water purification. No GPS means planes can't fly safely. Refrigerated food supplies spoil. Banking systems crash.
That sounds incredibly fragile. Do we get any kind of warning?
Thankfully, yes, this is not like an asteroid that can sneak up on us. We know the sun runs on a roughly 11-year cycle of activity.
So we know when the risk is highest.
Exactly. And more importantly, we have satellites watching the sun 24/7. There's one called DSCOVR, the Deep Space Climate Observatory, that sits between us and the sun, acting as a kind of early warning system.
A solar tsunami buoy.
That's a perfect analogy. So if a massive CME is launched in our direction, that satellite sees it first.
How much of a warning do we get? What's the actionable window?
We get between 15 and 48 hours before it hits Earth. That's the window.
The window to do what?
To implement a global protective shutdown, to power down the most critical parts of the grid, isolate those big transformers, and get emergency services ready.
Hold on. 15 to 48 hours. Is that really enough time to get major countries, maybe even rival nations, to agree to shut down their entire infrastructure?
And that, right there, is the multi-trillion-dollar question.
The technology isn't the problem. It's the human element, the politics.
The engineering solution is pretty well understood. We know what to shut down. But the political and logistical challenge of coordinating a global shutdown in less than 2 days, that's maybe the biggest vulnerability of all. Our lack of, standardized global protocols is a far bigger risk than the sun itself.
Okay, now we're moving into the realm of things that feel like pure science fiction. The stuff that fuels our deepest, most existential fears.
Black holes and gamma ray bursts.
They are real phenomena, but they feel so alien, so powerful.
They are absolutely real. But it is vital that we ground this part of the conversation in probability, because the chance of harm from these things is, thankfully, infinitesimal.
So let's start with wandering black holes. The fear is always that one will just drift by and suck us in.
Like a cosmic vacuum cleaner, yeah. That's the common image.
But that's not how it works.
No, the physics is a bit different. First off, the nearest known black hole is thousands of light years away. They don't typically just, wander the cosmos as vagabonds. But let's say a rogue one did pass through our stellar neighborhood.
Okay.
It wouldn't magically aspirate us. The problem is its gravity, its sheer mass. Think of our solar system as this beautifully organized, predictable machine. If you suddenly introduce an object with immense gravity, it throws everything into chaos.
It would catastrophically disrupt the orbits of the planet.
Exactly, sending Earth and the other planets careening off into new, chaotic trajectories. So, still civilization ending, but in a gravitational way, not a getting eaten way.
And again, the probability is reassuringly low.
Vanishingly small.
Okay, let's move on to the other cosmic monster. Gamma ray bursts.
Yeah.
GRBs. The sources describe these as maybe the single most powerful events in the entire universe. What are they?
I like to call them cosmic lighthouses of destruction. They're these hyper-energetic jets of radiation that are fired out when, for example, a massive star collapses into a black hole or when two neutron stars merge.
And the energy output is just staggering.
It's hard to comprehend. A GRB can release more energy in a few seconds than our sun will produce over its entire 10 billion year lifespan. But, and this is a huge, but that energy is focused into two very narrow beams.
Like a lighthouse beam.
Precisely. And so for it to be a threat to us, two things have to happen. It has to occur relatively close by, within a few thousand light years, and that beam has to be pointed directly at Earth.
What's the actual mechanism of the threat? It's not a physical blast, right?
No, it's the radiation, the intense high-energy X-rays and gamma rays. If a beam hit our atmosphere, it would basically rip apart the nitrogen and oxygen molecules.
And what would that do?
It would create huge amounts of nitrogen dioxide. This gas would blanket the Earth in a kind of perpetual orange smog. But far more critically, it would completely destroy our protective ozone layer.
And without the ozone layer?
Life on the surface, any life, would be exposed to lethal levels of UV radiation from our own sun and from space. It would trigger a mass extinction, a catastrophic one.
That's terrifying. But let's bring it back to that idea of tranquility, of perspective.
Yes. We have to. The universe is unbelievably vast. We are in a quiet, stable corner of our galaxy. The probability of being in the crosshairs of a GRB is, wow, like winning the worst lottery imaginable several times in a row.
So it's a genuine scientific phenomenon, but not something that should keep you up at night.
Exactly. We should look at it with scientific curiosity, not with dread.
So if we pull all of this together, the asteroids we can track, the solar storms we can prepare for, and the cosmic monsters that are almost certainly not a threat, what's the big takeaway?